Hello, everyone. Good morning. Welcome back. I hope you enjoyed the talk by Professor Stuart Russell. We were very excited and honored to have him with us for this third edition of MoroccoAI conference. And now we move to the first keynote speaker of today, who is Professor Mounir Ghogho, an exceptional researcher based this time in Morocco. So Professor Mounir Ghogho received his PhD degree in '97 from Institut Polytechnique of Toulouse, France. He was an EPSRS research fellow with the University of TICLab from September '97 to November 2001. In December 2001, he joined the University of Leeds, where he was promoted to full professor in 2008. While still affiliated with the University of Leeds, in 2010, he joined the International University of Rabat, UIA Rabat, where he is currently Dean of the College of Doctoral Studies and Director of TICLab. He is a fellow of IEEE and the Asia Pacific AI Association. He is also a recipient of the 2013 IBM Faculty Award and the recipient of the 2000 UK Royal Academy of Engineering Research Fellowship. He has coordinated around 20 research projects and supervised over 50 PhD students in the UK and Morocco. And he served also as associate editor of many journals, including the IEEE Signal Processing magazine and the IEEE Transactions on Signal Processing. We are very, very happy to have you with us, Professor Mounir Ghogho, and thank you again for accepting our invitation. And yes, Prof. Mounir Ghogho will talk to us about efficient AI, frugal AI. So yeah, Prof. Mounir, the floor is yours, and thank you again.
Thank you. Shall I start?
Yes, please. You can start sharing your slides.
Okay, thanks, Juan, for the kind introduction. I'm happy to participate to this year's edition of MoroccoAI Annual Conference. And I'd like to take this opportunity to congratulate you for the work that you do in the MoroccoAI team. Excellent work, and keep it up, and I wish you all the best. I need to share my slides. Can you see my slides?
Yes, yes, perfect. Thank you.
Okay, what I'd like to talk to you about today is efficient AI systems, efficient deep learning. There are two reasons why I wanted to talk about this. The first one is that I'm obviously interested in this topic, and we're involved in a project, a European project with some academic industrial partners, and trying to develop AI-based solutions for edge applications. And the second reason is that I think this topic deserves more attention from the Moroccan research community, not just from the application perspective, but also from the theoretical research perspective. And I hope that this presentation will trigger some interest. Slides. Okay, so why frugal? Well, I'll start to talk about a more general concept, which is frugal AI, before talking about efficiency. So why should we care about frugal AI? And I've listed a number of reasons. I'll start with environmental sustainability. And we know that the ecological footprint of large AI systems is very high. We knew about the carbon footprint, but recently there's a paper that had been published where the authors have estimated the water footprint of large AI systems. I think it was ChatGPT. And the estimate was about half a liter of clean water that was consumed for every 5 to 25 question conversations with ChatGPT. I think that was 3.5. The consumption of water for GPT-4 was not that, but I assume that it's way higher than that. And the training of ChatGPT 3.5 or 3, I can't remember exactly what version it was, the amount of water was staggering. It was enough water to fill a couple of thousands of Olympic swimming pools. So the water is used to cool the data centers, Microsoft data centers, but also to locally generate electricity. It's really an issue. And what makes matters worse is that to reduce the carbon footprint, they're supposed to go to locations where there is plenty of sunshine. But the problem is that in those places, the water, the clean water, is scarce. So there's a kind of there is a negative association between solar energy availability and clean water availability, as seen on this figure on the right-hand side. So, the authors talk about whether to follow the sun or to unfollow the sun. So it's a big concern about sustainability of these large AI systems. So that's the first reason why we should investigate Frugal AI. The second reason is cost-effective global accessibility. And I think here, this is a central goal of Frugal AI, to reduce economic barriers to access to AI tools, to make them more accessible and more cost-effective for a broader range of applications and users, and also may play a role in empowering small and medium enterprises to have access to AI tools, and stuff like that. Because in general, large corporations have access to advanced technologies, and so to make these technologies available for small and medium enterprises, we have to make AI affordable, and Frugal AI can help with that. And then the third reason is technological sovereignty. I think it's important for a country to have some sort of control over the digital infrastructure and systems. I think with Frugal AI, we can make this possible by giving the opportunity not only adopt, but also adapt AI technologies in more economically viable manner. Also, I think Frugal AI is not just about cutting costs, but also it could be seen as a pathway to empowerment and strategic autonomy. So by embracing Frugal AI, nations can foster the development of local expertise, reducing reliance on external expertise and proprietary systems. So I think Frugal AI holds the promise of not just economic efficiency, but also the cultivation of a distinct national technological identity, and I think that's important. The third reason is edge AI applications, where we have to develop AI systems with low resources, either for the constraints of the application. We have some applications where we have to have low latency, and also for privacy issues. Sometimes we can't use the cloud to do the inference. And the last reason, and not least, is academic research survival. I think Frugal AI levels the playing field, because we start from basically the premise that we don't have a lot of resources. How can we develop powerful and accurate AI systems to address a number of issues? Okay, so what are the design principles of Frugal AI? So here there are four elements. The first one is efficiency. This is what I'm going to focus on in this talk. Efficiency is about optimizing performance while minimizing the resource usage. But also we have affordability, which is crucial for Frugal AI, This is to ensure that that AI solutions are not just efficient, but also economically accessible. We have adaptability. So this highlights the system's ability to adjust to changing conditions. And the last one is obviously sustainability. We have to make sure that AI systems is sustainable in the long term. But I'm going to focus on here is efficiency. And efficiency, we have training efficiency and inference efficiency. Well, data efficiency sometimes is included in training efficiency. I'm going to focus on inference efficiency, even though, as you will see, for some models, we have to train special architectures. Okay, so this is my vision of the research directions for efficient inference. I have here 4 components. One of them is well known, which is model compression, and probably the other 3 are less well known. I'm going to say a few words about all of these four components. And I hope that by presenting some of the results, I won't have time to go into the technical details, but I hope that this will trigger some interest within young Moroccan researchers. So we have model compression, dynamic neural network, predictive coding, and neuromorphic computing. I don't think I have time to talk about this. But anyway, these are the 4 research directions that I think are interesting if we wanted to pursue efficient inference. I haven't included here the hardware acceleration, which is also a key aspect for efficient inference, including for neuromorphic computing. Okay, so I'll start with model compression. Okay, so model compression, I'll start with quantization. So quantization is the process of transforming the weights of a model into representations of a small number of bits. This involves some rounding and clipping of the numbers. So in this space, there's a lot of work that has been done. This is still a very active area of research. Okay, so I have a problem changing slides. So there are different categories of methods that have been proposed for quantization in deep learning. We have what we call quantization of word training. So this is when we include the quantization in the training process. And we have post-training quantization. Sorry, it's about this. Okay, so in quantization word training, this requires retraining the issues with the gradient because we have non-differentiable operations when we do rounding and clipping. So the training is quite unstable. And this is particularly an issue when we have large language models. So there's another family of methods that have been proposed more recently where we do training after the training, sorry, quantization after the training. This is what we call post-training quantization. So a method called GPTQ, GPT has much to do with GPT LLM. This is gradient-based post-training quantization. So this is an interesting method that has been proposed recently where quantization is done layer-wise and post-training. So basically, we use here some calibration set to do the quantization. So this is as opposed to one of the methods that have been published before, which is referred to as data-free quantization. We just use the model that has been trained and try to quantize without any data. Data-free quantization is was was okay, but the issue was performance, because even though we managed to reduce the number of bits, but performance was quite far away from the initial model. So as a middle ground between the error-free quantization and quantization we're training, this method GPTQ, which was proposed, which uses a calibration to do post-training quantization layer-wise. So the performance, I show you some of the performance of these methods. So here, the authors have, this is a recent paper where the authors have shown the performance of LLM, this is perplexity of the model, versus the number of parameters in billions. They show that by increasing the number of parameters, we can have the same performance with 4 bits instead of 16 bits, for example. So which means that we can reduce a number of bits to represent the model quite significantly without undermining performance. Another result which I find quite interesting that's been published recently, where the authors have looked into the scaling laws, how the performance behave as we increase the number of bits to represent the weights. So this is the total number of bits. So that this is a function of number of elements, number of parameters, number of weights, but also the number of bits that we have for each weight. And it seems that having 4 bits is optimal. This is what is shown on this figure here, where here you have 4 bits in orange, and in blue you have, I think, 3 bits and 8 bits underneath. So this is quite intriguing result that 4-bit precision seems to be optimal for total model bits. So this is on a zero-shot accuracy. I mean, the model was tested on tasks that have not been used in the training. Okay, so a lot of interesting results and work on quantization. It's still a very active area of research. Then we have pruning. The same thing here. There's a number of good methods that have been proposed for pruning. We have unstructured and structured pruning. And again, should we do pruning while we train the model, after training the model? And for the same reasons I mentioned before, for large models, it's better to do this after the training and hopefully preserve performance. Again, data-free methods were proposed and other methods based on calibration set, the same as for quantization, using, again, layer-wise pruning and using a calibration set. And interesting method called sparse GPT was proposed. I'll skip the technical details, and I'll just show you the results here by doing this layer-wise pruning, which is post-training pruning. They've shown here that they can reduce the number of parameters by half without undermining performance when using this method here, because the method here is quite sophisticated. In addition to optimizing the mask here, whenever we remove some of the connections, we have to update the other weights. Otherwise, the performance is poor because there are correlations between parameters. But anyway, interesting paper and interesting results. And then we have low rank approximation. So this is using things like SVD to approximate matrices with low rank approximations. This is quite interesting, and there's some recent results, even though initially the performance was quite poor because we started the training by enforcing the low rank assumption. But later work has shown that if we start with a full model and then we alternate between low rank approximation and full training, then we have better performance. But anyway, this is still an active area of research, which is quite interesting because it reduces the number of elements that you can use to do inference. For example, we have more compact convolutions. Okay, and then we have knowledge distillation. I'm going to skip this. This is learning a small model for a large model from a large model. But the problem with these methods is that once deployed, the computational complexity of the static model is constant at inference. We perform compression of the model to reduce the complexity of the model, but the model that is used for inference is always the same. So the question is, can we do better than that? So that brings me to the second research direction, which is dynamic neural networks. Okay, so in typical real-world scenarios, we know that input samples exhibits different levels of complexity, of difficulty. So it is well known that shallow networks should accurately classify standard or canonical inputs or easy inputs, whereas larger models, more complex models, should be used for more complex samples. You have here on the right-hand side different images of a cat. So here it's clear that classifying the top images is very easy, whereas the figures in the middle is slightly more difficult. But here is very difficult. We have to look for this thing that we have inside the square, thing that has no beak. So it means that probably the model that we should use to classify the image should depend on the complexity or the hardness of the image. And that's the idea behind adaptive inference. And if you look at the performance of classification methods, let's say image classification versus number of parameters, then you have a sharp increase in performance with the depth of the model, and that's because we learn interesting representations, internal intermediate representations of the images and so on. But it seems that there is a diminishing return of performance beyond a certain level. So there are different reasons to this. One of them could be just training large model or deep models is more difficult. We have gradient issues, even though some methods have been proposed for this, residual networks and the like. But I also think that the issue is that we have in the data set difficult samples, and probably the proportion of those difficult samples is small compared to easy samples. So we have some sort of heavy tail distribution of hardness of the inputs. So that's the diminishing return that I was talking about. So here I've shown the performance if we take just easy samples and if you take hard samples. Okay, so adaptive inference. So refers to the idea of processing easy samples with less resources than hard samples. That's the bottom line. So what are the advantages? Obviously, we have efficiency. We can save resources in terms of energy consumption. We could have also a low latency for easy samples, and we could have also low memory footprint at the inference stage. Data efficiency, adaptiveness, and increased interpretability. I can skip all these things. So what can be dynamically changed? We can change the structure of the neural network by adding, removing connections on the fly. This is runtime modification of the model. And we can also change the parameters of the model. There's also a lot of methods that have been also proposed for this. The parameters that are used at inference could depend on the input. There is also some method that predict the weight depending on the inputs. Anyway, these are the two things that we can change: the structure and the parameters. What are the input adaptation strategies? We have sample-wise strategies. This is where we change the structure for different samples. either the architecture or the parameters. We have a spatial-wise strategy where we use the observation that when we do, for example, image classification, not all areas of the image contribute equally to the classification. So we can select or choose the areas that we should focus on and allocate more resources and so on. So this is what we refer to as spatial-wise strategy. And we have temporal-wise strategies where we perform adaptive processing along the temporal dimension for sequential data such as text, audio, and so on. The adaptation mechanisms, I can skip this, attention module, gating functions, dynamic operators, and also dynamic activation. The slope of the activation could be also adaptively changed. But I'm not going to talk about this because most of these methods, the purpose is not efficiency, and it's more about performance. So I'm going to focus on something that tries to reduce the consumption of resources. And this is what we refer to as early exiting. So early exiting allows confident early termination of the computation using decision blocks. So we have different schemes for this. We have a cascading of models. So here we have different models. We start with a simple model, and then we measure the confidence that we have in the results. If the confidence exceeds some threshold that we will have defined, then we exit. Otherwise, we go to the second model and so on. So this is what we call cascading of models. So by the way, the idea of dynamic inference is not new. It's been around for quite some time. So traditional methods were based on ensemble models where we have different models and we choose which model to choose to use for inference depending on some features of the input. But that was done before deep learning, the modern era of deep learning. So this has been revived basically for. So that's the first strategy of early exiting. So the decision block here consists of a classifier and then a kind of a router. Sorry, so here the decision block is just a router, decide whether to go to the second model or not. The second scheme is early exiting with intermediate classifiers. So the problem with the previous model is that if we decide not to exit, then we have to start the processing from scratch. Whereas the second scheme here, we have intermediate classifiers. So we go through the network, the deep network, and then after a few blocks, we apply a classifier, and then we decide whether to exit or not, depending on some score that would have to be determined. And then if we don't exit, then we go to the second subnetwork and so on. So it means that here we don't waste the resources that have been used in the previous steps. So the decision block in this case consists of a classifier and a router. So here, the earlier we exit, more efficient the inference would be. I mean, the less resources would be used for the classification. Another variant of this second scheme is resolution adaptive schemes, where we start from the observation that when we have easy samples, we don't need to have a high resolution, so we could lower the resolution of the image and then apply a model, and then if the classifier gives us some confident result, then we exit. Otherwise, we go to the second, but here we use feature fusion. The feature that will have been developed and computed in the first stage could be fused with the the feature that would come from the image with higher resolution and so on. And that, again, that can show so this is what we refer to as resolution adaptive. And there are other schemes, other variants of scheme 2, where instead of looking at the classifiers independently, we can use the previous classifier and then every time decide based not just on one classifier, intermediate classifier, but also on the previous classifier. This is a method that's been proposed in proof of concept. We could also do spatial wise early exiting. So it's interesting work where they decided on when to exit for each pixel. This is for image segmentation. So for some pixels, we don't have to go through many layers to do the classification. So we can exit early. So this is so in this paper here, they found that border pixels are in general more difficult, so they require a deeper network, unlike other pixels. So quite interesting. So these are the results. You can reduce the consumption, the complexity of the model. And then we can do dynamic sequence processing. So this is acting on the temporal dimension. So if we have, for example, a sequence of tokens, for example, RNN is based on feeding, updating the hidden states based on previous hidden state and the current input. So we may decide to have a route or an agent that would skip basically going through the fixed RNN, because we can decide that this would not be useful. And that's one way of doing this. This is what we call skipping the update. But we can also do selective updates where the model that we use to update depends on the previous hidden state and the input, the current input. So sometimes we talk about skimming RNN, where we update part of the vector. We could use a different model. We could have here a different model and choose the one on the fly. So there are other methods also where we do early exiting by deciding to hold the processing, for example, sentence, if we are confident about the classification of the sentence, if we do sentiment analysis. So if we have enough evidence that we don't have to process the remaining tokens, we can exit and classify. And this has early exiting has also been recently applied to LLM. So the goal here was to decide on the number of layers that we should use in the transformer for each token, while preserving the performance textual consistency of the output with the full model. Interesting paper to read, published I think last year. And they've shown that potentially we can, on average, use only 1.5 layers per token instead of 8 layers without lots of performance. So this is using early exiting at the token level, which is quite interesting. Adaptive scheme is, instead of doing early exiting, we skip layers. This is also possible, but skip that. So the training of dynamic neural networks is an issue. I think I'm running out of time. Sorry, we have, just quickly, we have layer-wise training where we fix a layer, and then once we have trained the first layer, we move on to the second layer. Layer here includes also the classifier. The problem is that this is short-sighted, and we don't learn representation that may be useful for later layers. We have the second strategy where we train the backbone separately, and then we train the internal classifiers afterwards. And we have joint training where we try to join to design the different classifier using some combination of the losses. And skip that. So we have applied this within the European project that I was telling you about to audio denoising by using early exiting. We started off with a model called SNet2, and we modified the structure of the model, and we applied early exiting with the goal of preserving the same performance. In audio denoising, the loss function is well, have to take care of the phase and also the magnitude separately, and then we combine the different losses of different classifiers. And then here, this shows the result that we've obtained. We've shown that we can reduce the complexity without undermining much of the complexity, and reducing the number of parameters, that we use, and also the number of flops. The third topic that I'd like to talk about briefly is predictive coding. Predictive coding.
Professor, maybe we'll have just like 2 minutes to wrap up.
Oh, sorry.
Yeah.
Okay. So predictive coding, this is also interesting direction. We're known in signal processing for interpolation, compression, noise reduction. Has recently been applied for speech synthesis using neural networks. Again, the idea here is instead of processing or predicting, the sample would predict the error, the prediction residual, the difference between the sample and the predicted values. So the error would have lower amplitude, and therefore we can reduce the number of bits, and also the size of the network that can be used should be small, and so on. So here they've shown for speech synthesis based on NPCnet, they've reduced the number of blocks quite significantly. There is some grounding of this in computational neuroscience. I don't have time to talk about this. Okay. So we've applied this predictive coding and combined this with the early exiting by optimizing the number of cycles that we do in the predictive coding setting. And again, here we've shown that for different data sets, we can exit with a small number of cycles and therefore reduce the complexity of the model. Sorry, unfortunately, I don't have time to go through this. I had underestimated the time required for each section. I'll skip this. So this is the European project that we're working on with different partners, in academic and industrial partners. What we're supposed to do is to work with Jabra on deep audio processing, signal denoising, bandwidth extension, signal quality prediction. We work with Bosch for acoustic perception for autonomous cars, developing efficient AI algorithms. And we also work with Thales on segmentation object detection for satellite images. And this project is still ongoing. So the conclusion is that I think it's important to work on frugal and open source AI. So this is the motto, FOSSAI, F for frugal, not free. Because I've seen this acronym also in with F referring to free, but here for me, F should be frugal and open source AI for more inclusive and responsible AI. And thank you for your attention.
Thank you very much, Prof. Mounir Ghogho, for this excellent and informative presentation. I actually enjoyed personally the presentation as I work in AI and climate, and I know that it's very important to work with models that will not add more carbon emissions. So it was really, really interesting to me personally also. So as time is really pressing, we will take just maybe 2 questions. So yeah, you can maybe please stop sharing the screen, and I can start with the first question. So the first question is the following: how can organizations strike a balance between cost effectiveness, frugal AI, and performance when implementing those efficient AI solutions?
Well, I think first we have to master the issues, the techniques for efficient AI. First, we have to try to get the maximum out of what we have, given the resources. So this notion of efficiency is important because we have limited resources. Given the resources, how much can we get out of those resources? That's the first thing that we have to do. Then, of course, we know that by increasing resources, we potentially have better performance, but that depends on other factors. But we as researchers, what we have to make sure of is that we make AI as efficient as possible. Resources, that's something that has to be also discussed with other stakeholders.
Yeah, thank you. The second question is the following. What lessons have you learned from developing Frugal AI solutions in your research in Morocco, especially in the Moroccan context?
But I enjoyed the topic, and I hope that more young researchers in Morocco can start working on these topics, not just from the application perspective, as I said, but also from the theoretical research perspective. That's why I wanted to talk about some of the interesting results that have been published. So I think it's, as I said, it's also about academic research survival. Frugal AI levels the playing field. You know, we have big companies that have a lot of resources and you can't compete with them. So, but if we work on Frugal AI, basically we start from the premise that we don't have a lot of resources. So we level the playing field. So it's about coming up with innovative algorithms to have better performance, given the resources that we have. And I think this is doable, particularly for developing countries such as Morocco. We don't have a lot of resources, but I hope that more researchers could start working on efficiency, while probably hoping to have more resources also available in the country.
So yeah, I do have a last question. It's a bit related to this previous question. It's about your opinion on the level of awareness in Morocco of the energy challenges, especially when
sorry, say it again, please.
Of the awareness of Moroccans about the energy challenges and how Frugal AI can contribute to reducing the energy footprint. I think it's more related to the other question also.
I think by talking to young people, we don't seem to have high awareness about climate issues in Morocco, unlike some developed countries. Well, there are probably reasons for this, but it's not high on the agenda of young people anyway. But it's in Europe, for example, I know that there is a climate anxiety that is related to the climate. I mean, young people imagine all sorts of things in the future, which causes anxiety. I mean, we don't want that, obviously, but we want people to be, particularly young people, to be aware of these issues. There's also AI anxiety, which is also something that's becoming quite popular also in developed countries. People worrying about AI and AI will take all of our jobs, and what about creativity and innovation of humans? And so that's also another issue that
yeah, we tend to be very optimistic
about. And it's education is key here, to educate people about AI, to demystify AI to young people, to tell them what is possible and what's not possible, and to show also the good things about AI.
Yeah, absolutely. So yeah, maybe some few words for the MoroccoAI community. Just last words in French or English.
Yeah, it's there's a lot of potential and a lot of intelligent people and researchers, and I think sometimes what is missing is probably some guidance and focus on important things. But I think through events such as the one that we're participating in, I mean, obviously we can raise awareness and guide those young researchers basically to work on relevant issues. But I'm optimist that I'm an optimist that we have the potential to take the challenge of contributing to AI in the future. But we have to organize ourselves, and also we need resources. That's definitely something that's that is crucial. But anyway, the ecosystem, as far as human resources is concerned, is there. I think we have a lot of capable young people. What is missing probably is coordinated efforts, basically, to make a real contribution to the field. And I thank you guys for the work that you're doing. Really
Many
excellent.
thanks.
You're growing, and
Thanks to you. Thanks to you, Professor.
You know, you're attracting a lot of good speakers, and you do a lot of good work. I'm really proud of you. All the best.
Oh, it's a pleasure. It was a pleasure having you with us. And thank you very much to all the attendees also. Please stay with us for the next keynote with Professor Hamid Bouchiri. And yes, thank you again, Professor Mounir Ghogho, for accepting our invitation.
Bye.
See you. Bye-bye.